Okay, so introduction to organic chemistry. The term organic means that it has to do with living things. That's sort of the old way to think about the term organic. Now we think of organic chemistry as being the study of carbon-based compounds. And even though we just focus really on the element carbon, hydrogen, oxygen, and nitrogen in organic chemistry, there are more compounds based around carbon than all the other elements combined. And that's because of carbon having 4 valence electrons. Because it has 4 valence electrons, it tends to form 4 covalent bonds. So with our dot structures, you should have been pretty familiar with drawing carbon with the 4 unpaired electrons. And then that means that we're going to end up drawing a lot of Lewis structures where carbon forms 4 covalent bonds. So it shares 4 pairs of electrons. That, combined with the fact that carbon is a relatively small atom, it has a strong attraction for electrons compared to other elements that have 4 valence electrons. And that means it forms really strong covalent bonds with hydrogen, oxygen, and nitrogen. So you end up with lots of different molecules, relatively stable. Carbon can also form chains with itself, thousands and millions of atoms long chains. So the carbon backbone of a lot of molecules is really important. And also carbon can form rings. So you can get molecules where the carbon is bonded around with itself in rings, and actually you can have whole sheets full of rings. You can have rings connected to rings connected to rings. So there's amazing complexity that you can get with just a few elements. And it really has to do with carbon's ability to form so many covalent bonds. It helps it be a great connector of other atoms together. But with that great complexity means that we have to be really careful when we're looking at structures. So here are 5 molecules, and at first they may look like 5 unique molecules, but actually molecule 1, molecule 3, and molecule 5 are the same. And I can tell because they all have 3 carbons in the chain of the molecule, and then they have an O to H at the end of the molecule, and that's always connected to the end carbon. So in this one, it's shown here. In this one, it's shown pointed up, but that doesn't really change things. The O is still bonded to the end carbon. It's just been drawn pointed up instead of to the side, and that doesn't change what molecule it is. And in 5, we've just pointed it down. So there are going to be different ways, every student, every person is going to draw the molecule slightly differently, and it doesn't mean that it's a different molecule because it just looks a little bit different. The key is which atoms are bonded to which other atoms. And so the difference is in molecule 4, the OH is bonded to this second carbon instead of being bonded to the first carbon. So when we look at these carbon chains, we're going to start numbering them. And so the number carbon that a group is attached to, or that an atom is attached to, changes things. So this molecule is different than this molecule because the OH is attached to the first versus the second. And then in this molecule, it's the most different because in this one, there's actually no O to H at all. All the other ones have an O to an H bond, but here we have only C to O and then O to C. So the oxygen is in between 2 carbon atoms. And so that makes it a different molecule as well. So when you're trying to spot different molecules, all of these, by the way, are C3, H8O. There's actually a lot of different ways that you can draw C3H8O. So you need to be careful. These chemical formulas become less and less helpful as the molecules get bigger and bigger and when there's more and more ways to put them together. Okay, moving down. The molecules that we're going to be most focused on, because they are the molecules that make up most of oil and natural gas, are the alkanes. The alkanes are the simplest class of organic compounds. They are hydrocarbons, a term that we heard early in the unit, which means they're only made of carbon and hydrogen. And they're said to be fully saturated. And that word in this context means that the carbons are all single bonded so that they have as many hydrogens attached to them as possible. So every location around the carbons is taken up by hydrogen atoms. And so in chemistry, we say that this molecule is fully saturated because it has as many hydrogen atoms as possible. All of the alkanes also follow a general rule. There's basically a math equation that tells us how many hydrogens will be in an alkane if we know the number of carbons. So if we start off and we think about the first just one carbon atom, the first alkane, well, the carbon has 4 unpaired electrons, and so that carbon is going to make 4 bonds, and we know that hydrogen only ever makes 1 bond. So the simplest alkane is CH4. Now, how do we use this general formula that's up here? Well, if I plug in 1 for N, and then I do 2 times 1 plus 2, well, 2 times 1 is 2, plus 2 more is 4. So the formula when we have one carbon atom is going to be CH4. When I do this with 2, if I plug in a 2 for N, and then I do H is 2 times 2 plus 2, well, 2 times 2 is 4, plus 2 is 6. So I get C2H6. So if you're following along at home, I would have you pause the video when I say to, and then see if you can fill out the next 6, and then once you unpause the video, I will fill them all in. So pause now. Okay, now assuming you've paused and tried it on your own, they are C3H8, C4H10, C5H12, C6H14, C7H16, and C8H18. And you can see that once we do the first one, every time we add a CH2. So the difference between any 2 alkanes is 1 carbon and 2 hydrogens. Okay, so that's how we figure out their formulas using the general formula. How do we name them? Well, there are some rules for naming in organic chemistry. There's actually a lot of rules, but the root name of any organic molecule is based on the longest chain of carbon atoms, the longest continuous chain. And there's a root word associated with every number of carbon atoms. So 1 carbon atom is associated with the word meth, 2 eth, 3 prop, 4 bute. Those are the hardest ones to remember. Then once we get to 5, 6, 7, 8, there are more root words that you would have heard before, like 5 is pent, 6 is hex, 7 is hept, and 8 is oct. Now with ane, the alkanes, they're always going to end in ane. That's how we're going to know that it's an alkane. And again, what does it mean to be an alkane? It means you're only made of carbon and hydrogen, and all the bonds are single bonds. So we did these formulas up above. So I'm going to fill them in here. And then I apply the root name and the ending. So the first one was methane or methane. The next one is ethane. So eth tells me the number of carbons, 2, and ane tells me that it's an alkane. Propane, butane, pentane, hexane, heptane, and octane. And these probably sound familiar. Methane is the main component of natural gas. Propane is what we use in barbecue grills and in some of our Bunsen burners. Butane is a gas that's used in lighters. And then we have octane, which is octane. The octane rating of petrol, of gasoline, it's basically octane is the main component of petrol. It's a little more complicated than that. But that's the idea. So these should sound pretty familiar, and that's because these are the most important component molecules of oil and natural gas. Okay, now when we have small molecules, it's pretty simple, and we can use these condensed formulas like CH4 to represent this, and C2H6 represents that, and C3H8 represents this, propane. These are all nice and straight chained. The carbons are one after the other in a row. But when you get to 4 carbons, you start to actually have more than one possible way that you can draw them. So both of these molecules here, if you count them up, there are 4 carbons and there are 10 hydrogens, but they're actually not the same molecule because the atoms are connected differently. So these things are called isomers. And they're really common in organic chemistry because there's lots of big molecules, and there's many different ways that you can draw with the same number of carbons and hydrogens. Now the thing is you need to have a naming system that can name them both. So again, the rule was the longest chain. So in this one, the longest chain is 4 carbons in a row. So that gives us the root name bute. It's an alkane, so it's butane. And there's nothing else going on in this one. So this one is just called butane. In the next one, the longest chain is 3 in a row. There's 3 in a row. Now it's also 3 in a row actually if I circle it this way. That's 3 in a row. And it's 3 in a row if I circle it this way. So there's all these different ways that I can circle it. But what matters is that the longest chain of carbon atoms continuously is 3. So the word for 3 carbons is prop. So this one is actually called propane. But it's clearly not just propane like the one up above. This is propane because it has 3 carbons in a row. So this has its root name as propane, but I've ignored this carbon here. The word for 1 carbon is meth. So this one is prop, and this one is meth. And so meth is 1, prop is 3, and so if I include both of those in my name, they add up to 4, which is how many carbon atoms are in this molecule. So when I want to say that there's an extra carbon, and we call this like a branch, it sticks off to the side like a branch out of a tree. So we call it methyl propane. So if I saw this name, I would know that there's a 3-carbon alkane, so 3 carbons in a row, and then I would know that there's 1 carbon sticking off to the side. Now usually what we also include is we include a number. This one, if we include a number, is called 2-methylpropane. And what that number tells me is which number carbon along the chain is it attached to. So 1, 2, 3. Well, it's attached to the 2nd carbon. And so if I was trying to draw this, I would go, okay, well 1, 2, my 2nd carbon is here. So that's the one I need to stick the methyl group off of, the other carbon off of. And the thing is, once you've drawn the carbon chain, that's the hard bit, then you add the hydrogen atoms all around so that every carbon has 4 bonds and everything is single bonded. And so then we still get C4H10. So the molecule on the left is just called butane. The molecule on the right is called 2-methylpropane. Okay, let's try one more. If we're doing pentane and we want to draw all its isomers, you can pause the video and try it. The simplest one is always putting 5 in a row. Then we want to shorten the chain to 4. It's very easy to think you've drawn a different version of the molecule if you just like bend the chain like this, but this is actually the same as the thing above. It's still 5 in a row. I've just drawn it like an upside down L, so that doesn't count as a new molecule. And this doesn't count as a new molecule. It's still 5 in a row, right? 5 continuous. So that doesn't count as a new isomer. So what we've got to do is, if this is 5 in a row, so this is pentane, if I make it go down to 4 in a row, and then I stick 1 off the side, now I can't stick it off the first one because again, that's just 5 in a row. And I can't stick it off the last one because that would have been 5 in a row. So let's undo those things. I can stick it off one of the middle carbons. So if I put it there, now my longest chain is 4. So that's butane. And this is 1 extra carbon. So that's called methyl. And it's on the 2. It's on the 1, 2. Now you might say, okay, well, couldn't I add it over here? Can I add it to 3? And you sort of can, right? But I would say that's actually the same molecule. It's just been kind of flipped around. And the way I know is that if I number from this end instead, 1, 2, it's still on the 2nd carbon. You always, when you number these, 1, 2, 3, 4, or, sorry, let me do that numbering again so it's not in the same color scheme. So we can either number from right to left, 1, 2, 3, 4, or we can number from left to right, 1, 2, 3, 4. And there's 2 different options. I could call this 2-methylbutane or 3-methylbutane. And the rule is simply to always pick the lowest number possible. So that's why 2 would be the best name for this molecule. Now, so there's no other option where I have a chain of 4. So I could try to make a chain of 3. If I make a chain of 3, I can stick 2 branches off the middle carbon, and then I still have 5. If I add all the H's in to all these, I've been leaving out my H's, but if you actually draw them, you'd want to fill in all your H's like this. C5, and then there's still 12 H's. If I want to name this one now, the longest chain is actually 3. So it's called propane. And I've got 1 carbon here, and I've got a 1 carbon here. So this is a methyl. This is also a methyl. It's not an ethyl. Ethyl would be if we had 2 carbons in a row. Then we call it ethyl, but that's not what we have. So we have 2 methyls, and the way I say that is dimethyl. So this molecule is called dimethylpropane. If I want to include numbers, then let's number, well again, what number carbon is it on? 1, 2, 3, or if I number it this way, 1, 2, 3. Either way, I'm on the 2, so good, I'm on the second carbon. And there's 2 methyl groups. I need to tell you where they both are. So 2, 2, dimethylpropane. The 2, this is where one of the methyls is, and here's where the other methyl is. So if you include numbers, you need to include as many numbers as there are branches. So since there's 2 methyls, I need to include a number for each of them. And that is, it gets a little messy, it gets a little complicated, and yet it's actually really a very detailed, very well organized naming system so that we can name molecules with immense complexity.